this bunch of problems on simple harmonic motion uh, aimed at delivering all the basic ideas that pertain to simple harmonic motion and related stuff. So the first one is about a particle whose position vector is varying as I cap plus 2j cap a cos omega t, right? And we want to be able to check the kind of motion it is, right? Surely this is simple harmonic motion, but it's not taking place along the x-axis. It's taking place along a line like this. This is a point P whose position vector is I cap plus 2j cap. This is a point with position vector this is the vector r, right? Along this line there is simple harmonic motion with angular frequency omega. This is simple harmonic motion that's not taking place along the conventional x or y axis. It's taking place along a line which is this, right? Along a line that makes an angle theta such that tan theta is 2. Along this line the simple harmonic motion is taking place. Now just to figure out a few other things related to the simple harmonic motion. One, of course, the angular frequency is omega. Angular frequency is omega. Also the velocity of the particle is like dr dt, which is I cap plus 2j cap a omega with a minus sign sine omega t, right? Where does velocity become 0? At the amplitude position. Velocity becomes 0 at the amplitude position. Yes or no? So velocity is 0 when v is 0. It happens, say, at t equal to pi by omega. Say, for example, at t equal to pi by omega, right? Or 2 pi by omega, for example, right? Say, one of the instances, t equal to 2 pi by omega, right? And this must happen at an amplitude position. This must happen at an amplitude position. That means when you plug in t equal to 2 pi by omega here, then that will give me the position vector of the amplitude state. That will give me the position vector of the amplitude state. Yes or no? That means the position vector of the amplitude state is obtained at t equal to pi by omega or 2 pi by omega, even pi by omega, because even at t equal to pi by omega velocity becomes 0, and that is like I cap plus 2j cap into a cos 0, cos 2 pi, or cos pi minus 1, so that will give me the other state of amplitude. T equal to pi by omega and t equal to 2 pi by omega will give me opposite states of amplitudes about the mean position. Also, velocity will be maximum at the mean position, right? So velocity is v max. Speed would be maximum. Realize when t is pi by 2 omega, for example, when t is pi by 2 omega, right? So if you plug in t equal to pi by 2 omega here, if you plug in t equal to pi by 2 omega, you'll get the position vector of the mean position. You'll get the position vector of the mean position. So if you plug in t equal to pi by 2 omega, that's the point where v becomes maximum in magnitude. At this position, r would be the position vector of the equilibrium position or the mean position. So what happens? T equal to pi by 2 omega, this will become 0. This will become 0. So r becomes 0. That means it's simple harmonic motion about the origin. It's simple harmonic motion about the origin along this line. Along this line. Yes or no? Right? And again, you know, if you differentiate this again with respect to time, acceleration is dv dt. Acceleration is dv dt, which is like minus I cap plus 2j cap a omega squared cos omega t, right? And I cap plus 2j cap a cos omega t. I cap plus 2j cap a cos omega t is the position vector r of the particle. So this I cap plus 2j cap into a cos omega t. So this will become minus omega squared into the position vector r. So acceleration and position vector are related this way. This must be simple harmonic motion of angular frequency omega with mean position being the origin. Yes or no? Right? So here we have a ideal spring, force constant K, a mass m1 rigidly attached to the spring, and m2 just sitting on the surface of m1 horizontal, right? We want to be able to find the maximum possible energy of oscillation of the system, right? Now, first of all, let's understand some very basic premise of this physical situation, right? Say this was the state of natural length of the spring. This was the state of natural length of the spring. Do you realize this is not an equilibrium state? Spring force is 0. There is a net downward force on a system comprising m1 and m2, which is m1 plus m2 into g. So for sure this is not a state of equilibrium. This is not a mean position for this system of particles m1 and m2, right? So this is the natural length of the spring, but not equilibrium position. Obviously this pair would descend down, the spring would elongate, would exert an upward force which at some point would balance the weight, and that would be my equilibrium position for the pair, right? So the equilibrium position is this. This is my EP, or the equilibrium position, or the mean position, and let's say that happens at x0 below the natural length. And what happens in this case? The spring force kx0, just about balances m1 plus m2 into g. This is what transpires, right? And this x0 obviously will also be the amplitude, Now, once vibrations set in, once oscillations set in on this system, this pair could be above the equilibrium position at certain times and below the equilibrium position at certain other times, right? We'll have to first figure out, one, what would be the angular frequency of oscillation for this pair. Two, where is it most vulnerable to lose contact? Where is mass m2 most vulnerable to lose contact, above the equilibrium position or below the equilibrium position? We need to figure that out, right? So first things first, once it has reached this state, and from the equilibrium position, let's say after a while, it gets displaced by an amount x downwards, right? Then the spring force upwards is going to be k into x plus x0, upwards, and weight m1 plus m2 into g acts downwards, right? Do you realize kx0 is balancing m1 plus m2 into g, because this is an equilibrium position. Kx0 is about balancing m1 plus m2 into g. So now look at this state below the equilibrium position, x units below the equilibrium position, for example, right? So the spring force is k into x plus x0 upwards, weight downwards. Kx0 will balance this. So what is the net upward force? Kx is the unbalanced force. This is the restoring force acting on m1 plus m2. Yes or no? Because kx0 is balancing m1 plus m2 into g. Kx is unbalanced, right? X is the displacement from the equilibrium position downwards. The restoring force kx is upwards. That means the force constant for this oscillation is k. The force constant for this oscillation is k, right? And therefore the angular frequency of oscillation for m1 plus m2 together is going to be root k by m1 plus m2. That's the angular frequency of oscillation. The time period of oscillation is going to be 2 pi by omega, and so on and so forth, right? So that's established. One, this is going to execute simple harmonic motion with angular frequency root k by m1 plus m2, right? Now, say when this is displaced by an amount x units below the equilibrium position, what happens? Let me look at M2 alone. M2 is also executing simple harmonic motion with the same angular frequency as M1, right? Now, M2 is not directly connected to the spring, right? It executes simple harmonic motion for reasons different from what M1 experiences. M2 is experiencing two forces. What are the two forces that M2 is experiencing? It's normal reaction from M1, which is N upwards, and Mother Earth, M2G, downwards. Right? Yes or no? Now, the net force on M2 must be directed towards the equilibrium position. The acceleration of M2 is going to be omega squared into x upwards. Omega squared into x upwards, yes or no? So, writing the force equation for M2, which is like N minus M2G is equal to M2 into acceleration, which is omega squared x. Right? So, N then is like M2G plus M omega squared x, where x is the magnitude of displacement below the equilibrium position. Right? X is the magnitude of displacement below the equilibrium position, and below the equilibrium position, do you realize that N is always greater than 0? That means below the equilibrium position, the mass M2 is safe in as far as contact is concerned. It will preserve contact below the equilibrium position. It is not vulnerable to loss of contact below the equilibrium position. So I don't have to look at x units below the equilibrium position. Let me look at a state of this pair x units above the equilibrium position and examine if it is vulnerable there. So below the equilibrium position, it's safe. Any omega, any amplitude is good enough. There will be no prospect of loss of contact below the equilibrium position, right? So now above the equilibrium position, so this was my equilibrium position, right? And I'm talking of x units, magnitude of displacement x above the equilibrium position. This was M2 sitting neatly on M1, right? Its acceleration this time is going to be omega squared x, again towards the equilibrium position, downwards. What are the forces that will cause this acceleration? A difference of gravity and normal reaction. That's as far as M2 is concerned. Yes or no? So omega squared x is out of a difference of these two causes. So M2G minus N is M2 omega squared x. Now here's an issue which needs to be taken care of. N is M2G minus M omega squared x. This time, for a certain value of x, this could become equal to this, and there could be loss of contact. So it's vulnerable towards loss of contact above the equilibrium position. Yes or no? Right? So in order that it doesn't lose contact anywhere, I should make sure that this is always greater than or equal to 0. It will not lose contact. Right? That means the x above the equilibrium position must be less than or equal to g by omega squared, as you can see. That means its displacement from the equilibrium position must never exceed g by omega squared. That means if the amplitude itself does not exceed g by omega squared, then x will also not exceed g by omega squared. That means amplitude of motion should be less than or equal to g by omega squared for it to maintain contact. Maximum possible x, maximum displacement from the equilibrium position should be less than or equal to g by omega squared. Then any x will be less than g by omega squared. So effectively this boils down to having amplitude less than or equal to g by omega squared. And if this be the case, then realize that maximum is g by omega squared. And maximum amplitude would be a state of maximum possible kinetic energy of oscillation, because kinetic energy is proportional to the square of the amplitude, right? So this would give me the possibility of finding the maximum possible kinetic energy of oscillation. What would be the maximum possible kinetic energy of oscillation? Half of k into A max squared. That's the maximum possible kinetic energy of the system, right? Which is like half of k into A max is like, A max squared is like G squared by omega to power 4, which is like omega to power 4 is like k squared by m1 plus m2 whole squared, right? A squared max, G squared by omega to power 4, G squared by omega to power 4. Omega is this, omega to power 4 would be k squared by m1 plus m2 whole squared. Yes or no? That's a maximum possible kinetic energy. Again, as you can see, this is as good as half of G squared by k into m1 plus m2 whole squared. That's the maximum possible kinetic energy of oscillation of the system. Yes or no? Right? Make sense to all of you? Here we have an oscillator executing simple harmonic motion about the mean position, say the origin, having amplitude A and angular frequency omega. We want to find out the magnitude of average acceleration. Magnitude of average acceleration in half the time period. So first of all, time period is 2 pi by omega, right? Half the time period is going to be pi by omega. Half the time period is going to be pi by omega. In this, we want to find the average acceleration. So let me assume that the particle is at the origin at some instant of time, right? Then at the origin, it has maximum velocity, which is omega a. Recall that, right? Omega a is the velocity it has at the mean position, right? That is its velocity to the right at time t equal to 0, right? Now, it goes to the rightmost extremity and comes back to A. Now, when it comes back to A, the time taken would be half the time period. The time taken is going to be half the time period, and its velocity is going to be omega A to the left. And the time it takes for this to happen is going to be pi by omega, half the time period, right? So the average acceleration is going to be change in velocity by total time taken. Change in velocity, do you realize omega a minus omega a, right? That's a change in velocity. Omega a minus omega a, that's a change in velocity, divided by the time taken. Time taken is pi by omega. Yes or no? That's going to be the magnitude of average acceleration, which is 2 omega squared a divided by pi. 2 omega squared a divided by pi. That's the magnitude of average acceleration in half the time period. Got me? A pair of pulleys, and this is a thread, light inextensible thread with a mass m1 attached at one end of the string, right? There is another mass m2 connected at the end of the spring, which is integral with the pulley. Let's say this is the natural length of the spring. Say this is the natural length of the spring, okay? And the mass m1. So I'm just holding it here. And I release it, right? The mass m1 will descend down. If m1 descends down, do you realize this pulley along with this mass m will move up? The spring will get elongated, right? Now, let's say at a certain instant when this mass m1 descends by an amount x, m1 descends by an amount x, let's say it develops a velocity v. Yes or no? Also, would you want to believe from straightforward pulley considerations that this pulley would have moved up by an amount x by 2? This pulley would have moved up by an amount x by 2? Yes or no? So if this pulley moves up by an amount x by 2, if you've forgotten your pulleys, pull it back. Right? This mass m2 along with this pulley has to move up so that it can provide on either side a length x by 2 here, x by 2 here, freed, which features as descent of mass m1 by an amount x, right? And this mass, do you realize again that if this moves down by an amount x, it develops a velocity v. This moves up by only half the amount, so mass m2 would develop half the velocity because its displacement is half, right? So the velocity of m2 is going to be v by 2 because it's undergone half the displacement. Its velocity must have been from instant to instant half the velocity of m1. Now for this state of m1 and this state of m2 and the pulley, let me write down the energy expression. Let me write down the energy expression for the system, right? So kinetic energy first. Half m1 v squared, half m1 v squared, v squared, half m2 v by 2 whole squared. That's the kinetic energy of the system. Now there are two kinds of potential energy here. Elastic potential energy of the spring and gravitational potential energy of the two masses. So elastic potential, see the spring would have elongated by an amount x by 2. So the elastic potential energy of the spring is what? Half of k into x by 2 whole square. And then this loses potential energy. So minus m1 gx. This gains potential energy. So plus m2g x by 2. That's my energy expression. I need to find v dv dx, which is the acceleration. If I find that v dv dx is minus of a positive constant into x plus some other constant, then the positive constant that I'm talking of would be omega square for oscillation of the system. Yes or no? Right? So dE dx, that's the rule of the game then. dE dx. dE dx is going to be m1v dv dx plus m2, this is 8, so it will become 4 v dv dx. Do you realize that? This is 4 into 2, 8. And when I differentiate this, 2 v dv dx, that 2 will make this 4, right? m2 v dv dx. Then this is 4 2s are 8, 1 by 8, and then k and x square, where I differentiate, I get 2x. That will make this 4. kx. Yes or no? Kx by 4. And then this will become minus m1g plus m2g by 2. That must be 0. Yes or no? Differentiating with respect to x, right? And then this leads us to m1 plus m2 by 4 v dv dx, right? Clubbing these two together, v dv dx would be my acceleration for m1, right? That's equal to minus 1 by 4 kx plus m1g plus minus m2g by 2, right? And what's v dv dx? v dv dx then is minus k by 4 divided by m1 plus m2 by 4 into x plus m1g minus m2g by 2 divided by m1 plus m2 by 4, right? So this is my acceleration v dv dx, right? Which would be a positive constant minus of a positive constant into x plus some other constant. Then this positive constant must be omega squared. This must be omega squared, right? omega squared, therefore is k by 4 divided by m1 plus m2 by 4, which is like k divided by 4m1 plus m2. That's omega squared. Omega therefore is going to be square root of this. Time period is going to be 2 pi by omega. 2 pi by omega means root 4m1 plus m2 by k. That's going to be the time period of oscillation of the mass m1. Clear? Along the x-axis, its displacement as a function of time is given like this, right? And I want to find the maximum possible acceleration of this particle. Very good. I take 4 common here. This is 3 sine omega t minus 4 sine cubed omega t. 3 sine a minus 4 sine cubed a is sine 3a. Really nice, very good. So this is 4 sine 3 omega t. Yes or no? And what is the amplitude of oscillation? 4. Amplitude is 4 units. And angular frequency is 3 omega. Angular frequency is 3 omega. So 3 omega is the angular frequency. And maximum possible acceleration is angular frequency squared into amplitude, right? Maximum possible acceleration is angular frequency squared into amplitude. So 9 into 9 omega squared a. 9 omega squared a. A is 4. So that is 36 omega squared. 36 omega squared is the maximum possible acceleration, right? So this is a spring in its natural state. This is the natural state of a spring, unelongated, mass m attached to one end, smooth horizontal surface, that's where it's resting. Very slowly the mass m is pulled to the right and brought to A. Very slowly it's pulled to the right and brought to A. And it's released from this point. It's released from this point. The spring has got elongated. It will then pull the mass to the left, right? Very clearly, you understand that this is going to be simple harmonic motion, with this being the mean position, A being the amplitude, and omega being root k by m, right? The angular frequency of oscillation is going to be root k by m. Now, this is the extreme position. This is the mean position. The time taken to go from the extreme position to the mean position is pi by 2 omega. Remember that? Is pi by 2 omega. From the extreme position to the mean position we have discussed is pi by 2 omega, because the auxiliary particle describes an angle 90 degrees at the center at the rate of omega radians per second. So the time taken would be pi by 2 divided by omega, right? So the time taken to go from A to O is going to be pi by 2 omega. And that's perhaps given to be some T naught, right? That's given to be T naught. Okay. Clear? Now, so that's the first situation. Time taken to go from A to O is going to be pi by 2 omega. The next is where the mass is slowly pulled to the right and brought to B. The mass is slowly pulled to the right and brought to B. And it's at rest and released from this state. The elongation in the spring this time is 2A. This must be the amplitude state of the mass, and this must be the mean position for the mass. And 2a must be the new amplitude. The new amplitude is going to be 2a, but omega remains the same. Omega is going to be root k by m. Now, A is halfway between the two extreme states. This is the left end and this is the right end. No, I'm so sorry. This B to A, this is not the equilibrium position. A is not the equilibrium position. This is the equilibrium position. A is halfway between the equilibrium position and the amplitude position. A is halfway between the equilibrium position and the amplitude position. Have I told you the time it takes to go from an extreme position to halfway between the equilibrium position and the extreme position? Pi by 3 omega. Remember that? Pi by 3 omega. From the extreme position to the midpoint of the mean position and extreme position, the time taken is pi by 3 omega, right? So time taken this time to go from B to O is pi by 3 omega. Realize that the auxiliary particle describes 60 degrees at the center at the rate of omega radians per second. Go back to my previous class. So the time taken to go from B to A is going to be pi by 3 omega. Right? The time taken to go from B to O, from the extreme position to the mean position, is still pi by 2 omega, right? Time taken to go from B to O is going to be pi by 2 omega. Right? From the extreme position to the mean position is pi by 2 omega. Now, the time taken to go from A to O would be this difference. Time taken to go from B to O minus time taken to go from minus the time taken to go from B to A is going to be the time taken to go from A to O, right? So time taken to go from A to O this time in this is going to be pi by 2 omega minus pi by 3 omega, which is pi by 6 omega, right? Which is T naught by 3, which is T naught by 3, as you can see. The time taken this time to go from A to O is going to be T naught by 3. Clear? The next problem is about a particle of mass m, and it's connected to two springs. This is a spring with force constant k, and this is another spring with force constant 2k. And this is the natural state for both the springs. The mass m is in equilibrium in this state. That's given in the problem, right? And now very slowly, the mass m is pulled to the left by an amount x naught equal to mg by 2k and released from this position. It will now execute SHM. After a while, the mass m will pass through a point P, which is mg by 4k from the equilibrium position. I want to be able to find the velocity at this point P of this mass. Now, first things first. The two four springs, are they in series or in parallel? They're in parallel. So what's the equivalent k for the system? 3k. Right? 3k is the equivalent force constant for the system. Yes or no? So the angular frequency of oscillation for the mass m is going to be root 3k divided by m is going to be the angular frequency of oscillation of the two masses, of the mass. Right? Now, when it's slowly pulled to the left, it comes to this point where the spring has a compression and the mass is at rest. That means this is the position of rest for the mass m. This must be an amplitude state of the mass. And therefore the amplitude must be x naught. Amplitude of oscillation must be x naught, which is mg by 2k must be the amplitude of oscillation. Yes or no? Amplitude is mg by 2k. By 2k. Now velocity. This is my new x. This is say x equal to 0. This is x equal to 0, and this point is x equal to mg by 4k. I want to find the velocity at x equal to mg by 4k, where x equal to 0 is the equilibrium position. Hey, velocity as a function of x is given by omega root a squared minus x squared, right? Omega is known to us, right? What is omega? Omega is root 3k by m into root a squared. A squared is mg by 2k whole squared minus x squared. X for this point is mg by 4k whole squared. Whatever this turns out to be, that's going to be the speed of the particle as it passes the point P. Clear?